is to find acceleration. And something to keep in mind with acceleration, acceleration usually can be found one of two ways. Either by analyzing forces, because we have the equation acceleration equals net force divided by mass, or by using motion equations, because acceleration often appears in the motion equations. And in this situation, we have enough information to use the motion equations, and usually that's much easier. So let me jump into that. Usually I make a data table of the 6 different variables we normally encounter when we're doing a motion problem. So the initial position of this block, let's just arbitrarily say that it starts at 0. The final position then is below that, so negative 0.75. The initial velocity, we are told things start from rest. The acceleration is what we're looking for, and the time for this is 5 seconds. And one little hint here, if you have 1, 2, 3, 4 different variables in this data table, you will definitely be able to find one equation to solve it. Or in some cases, you might have to use 2. The only exception to that is if acceleration is 0. Sometimes you need to have 5 pieces of data. Anyway, I'm going to look for an equation that doesn't have VF in it, and that's this one, YF equals YO plus VOT plus 1/2 AT squared. So negative 0.75 equals 0 plus 0t plus 1/2 a times 5 squared. Shouldn't be too hard to solve for acceleration there. If only I had my calculator. Ah, here it is. Okay, so 0.75 times 2 divided by 25 is 0.06. So the acceleration is 0.06 meters per second squared. Actually, I should be careful about that. That's the absolute value of the acceleration. I wasn't really paying attention to positive or negative signs. Okay, so that's question A. So question B asks us for some reason to find T2. Oh, I know why, because we were sort of using the information from that object right there. Now, if you have to find a tension, we do not have any equations for tension, and that's because there is no one specific equation for tension. Basically, 100% of the time that you have to figure out tension, you're going to be using acceleration equals net force divided by mass. Of course, I shouldn't say 100%, maybe 99% of the time. And so, at this point, we probably should be careful about positive and negative signs. And that's one of the tricky things about a pulley problem, because the string changes the direction of the motion. This thing's going to move downward, this one's going to move upward, and then, of course, this thing's also going to spin. And we have to make sure all of the signs that we use for their equations are consistent with one another. What I like to do is I always like to stick with the practice of considering counterclockwise in rotation to be the positive direction. That has to do with the right-hand rule. If you take your right hand, you curl your fingers counterclockwise, your thumb points out, which is always considered to be the positive direction. So if I say that that is the positive direction, then being consistent with that means that going down on this side is the positive direction, and going up on this side is the positive direction. So that's a way to make all of those directions consistent with one another. So let's now go ahead and calculate the tension on this side. So anytime I use acceleration equals net force divided by mass, you always want to draw a free body diagram. I'm drawing a diagram of this object right here. So the downward force on it is gravity, mg. The upward force is tension, T2. mg is going to be equal to 0.5 kilograms times 9.8, and that's going to give 4.9 newtons. Now, direction-wise, we did say that on this side, up is positive, down is negative, and now the acceleration is actually in the downward direction. I mean, this one's going to fall, this one's going to rise. So that 0.06 that I calculated is actually a negative 0.06 using this scheme of directions. All right, so let's put it into the equation. Negative 0.06 equals T2 minus 4.9 divided by the mass, which is 0.5. And so if we solve that, that'll give us a value for T2. So let's see what I get there. Multiply by 0.5, and then add 4.9, and I get 4.87 newtons. T2 is equal to 4.87 newtons. So that's the answer to the second part of this question. Now, third part is find T1. And in the past, we've done problems where the two tensions are equal to one another. And that was because we were ignoring the mass and any friction of the pulley itself. And here we're not ignoring the mass of the pulley. And so in that case, the tensions do have different values on either side. So we really simply have to do another free body diagram, another acceleration equals net force divided by mass. So for object 1 over here, the mass, or I should say the weight is what I meant to say, is 0.46 times 9.8. So 0.46 times 9.8 is 4.508 newtons. And according to our scheme, that's going to be the positive direction. And here we have T1, and that's the negative direction. So now we can input that to acceleration equals net force divided by mass. It is going to accelerate this way, which is our negative direction. So negative 0.06 equals positive 4.508 minus T1 divided by 0.46. And so let's solve for T1. Take some time here with my calculator to work that out. And the answer I get is 4.5356. So as predicted, this tension is different than that tension. And I also, although I didn't mention it, would predict that this tension would be larger than that tension because the wheel is actually going to rotate in that direction, which means you need more torque in the clockwise direction than in the counterclockwise direction. So this is all making sense. Okay, next question was finding the magnitude of the angular acceleration. And here, very easy. We already have the linear acceleration of the string, and that's going to be the same as the linear acceleration of the outside of the wheel. So by simply taking the linear acceleration and dividing by the radius, we're going to get our answer. So 0.06 meters per second squared divided by how many meters one radius is, 0.05 meters. If you ever forget these equations, should you divide, should you multiply by radius, just think about the units. So really we're saying how many radiuses fit into 0.06. Mathematically, the m is going to cancel out. Let me do this on my calculator. 0.06 divided by 0.05 is 1.2. So that's 1.2 radiuses fit into that number. Now, technically, that's normally called radians, not radiuses, per second squared. So that's our answer. The magnitude of the angular acceleration is 1.2 radians per second squared. Okay, final part of this problem, looks like I have some room to do it over here, is find the rotational inertia of the object. Now, you may be tempted to say, oh, it's a disk, I'm going to do 1/2 mr squared. Well, be careful on two accounts. One, it never specifically says that it's a disk, and so you never want to make that assumption. And two, they didn't give us its mass, so we couldn't use that equation anyway. So the other thing that they've kind of set us up for, the other place where we see rotational inertia appear, is to use this equation, alpha equals net torque divided by I, basically the rotational equivalent of Newton's second law here. So we just figured out the alpha, it's 1.2. Now I am going to go back and not use the magnitude. I'm going to use the actual directions that we decided that we would use with this diagram here. And this thing is going to rotate in the clockwise direction. So that's the negative direction. Negative 1.2 is what I'm going to use for the angular acceleration. Net torque means add up the torques that are acting on it. And so basically two forces are exerting torques. One is the tension on this side. The formula for torque, let me just remind you what that is. Torque is radius times force times the sine of the angle between the radius and the force. So on this side over here, the radius of the disk is 0.05 The force, now that's the tension. It's actually the tension that's pulling on the disc. And you know, I violated one of my rules here, which is whenever I use a Newton's second law equation, I always draw a free body diagram. So let me do that real quick. I'm drawing a rotational free body diagram, so it's not just a dot, because when you're calculating torques, you need to know exactly where the forces are being applied. So on the one side, we have T1 pulling down, and on the other side, we have T2 pulling down. There are some forces that act on the axle, but they're not going to be exerting any torques because they're acting right at the axis of rotation, so they have no R, so I'm not going to get into those forces. Anyway, there's a radius on this side, there's a radius on that side, so now we can get back to it, where I'm calculating the torque due to T1. So the radius is 0.05. The actual magnitude of T1 is 4.5356. 4.5356. The angle, that's a 90-degree angle there, and the sine of 90 is 1, so I'm not going to bother writing that down. And finally, T1 would have a tendency to make this thing rotate counterclockwise. So that is a positive torque. All right, and so now how about the torque on the other side? Well, this is T2. It would have a tendency to make it rotate clockwise, so that's a negative torque. The radius is once again 0.05, and the force is what T2 is equal to, which is 4.87, so 4.87. So those are the torques that I'm adding up, and so the only unknown left in this equation is the rotational inertia. So let me take a few moments to pop those numbers into my calculator. Okay, and it looks like I'm getting an answer of rotational inertia of 0.0139, and the units for that would be kilogram meters squared.